This lesson is for section 9.4. Today we're going to be introducing you to a brand new conic section called the hyperbola. So our main objective for today is to be able to graph hyperbolas in the coordinate plane. So recall that a conic section is simply the intersection of a cone and a plane. Now we've already studied circles and ellipses, and now we're getting an introduction into hyperbolas. So as you can see here, a hyperbola sort of looks like a parabola, except for in this picture here we're missing part of this hyperbola. And so I found something online that I think does a really nice job of helping you visualize how we can create these different shapes by intersecting the cone with a plane. Okay, so in front of you is an interactive 3D conics grapher. Hopefully you can see my mouse and where I'm pointing, because I'm not sure. Sometimes with a web browser, it depends. It'll show it when I record my lesson, and sometimes it won't. But hopefully you're seeing that little yellow circle around my mouse. But right in the middle, it should say the conic type is a circle in green. And as you can see here, the rotation angle up at the top says 0 degrees. And that's because this plane that we're intersecting this cone with is parallel to the ground. Now, as I rotate this shape, you can maybe see it easier that it's a circle. If I give you a nice aerial view of that cone, like right on top, we do have a circle, okay? So let me move it back to that same position here. Okay, now I can adjust also the way that the length of the horizontal plane here that it's intersecting. I can just shift it. I'm just going to shift it back to where it was. Okay, and I can also move it down the cone, up and down that cone. So I can move it to the cone that is stacked on top of it. So we are seeing two cones stacked on top of one another, okay? Now I can also change the rotation angle as well. So as you can see, if I increase this angle, meaning relative to the horizontal here, I'm going to increase it to, let's say, 5 or I guess 20 degrees here. Now it's changing. The conic type, as you can see, says an ellipse. And if I rotate here, you can see that we are having an ellipse. It's elongated as opposed to that circle. Okay, so but just by changing the angle of that plane and the way it intersects the cone, we create new shapes. Okay, now let me rotate this a little bit more like that. All right. Now, if I increase that angle a little bit more, okay, now you're going to see that that shape is going to turn into a parabola. So here we're seeing it turn into a parabola, okay? And if I increase it even further, so as you can see, conic type parabola, as I increase that angle even further, now I get a shape called a hyperbola. All right, so there's your introduction to the other part of that other piece of this hyperbola here. So when you stack two cones on top of one another, your intersection is called a hyperbola once that plane starts becoming more perpendicular to the horizontal. So here I'm all the way at 90 degrees now, so the plane is completely perpendicular to the ground, and you're seeing the hyperbola here in red. Okay, so let's return now back to our note sheet where I have the formal definition of the hyperbola written here. I'd like you to pause and make sure that you do get this definition down on your paper. So the formal definition states that the hyperbola is the set of all points in the plane such that the difference, and there is a reason why I've bubbled this and put that in blue, the difference between its distances from two fixed foci is constant. So if you remember our definition for the ellipse, this definition here actually looks almost identical to the definition for the ellipse. It's just that this one word here, instead of saying the difference, it says the word sum. Now that one little change, however small it might seem, it actually makes a significant difference in the graph of your hyperbola versus a graph of an ellipse. It also changes the general equation as well. Okay, so one last thing before we actually start graphing hyperbolas on our own. I wanted to show you this online app here that I think does a really great job of demonstrating exactly how the points on the hyperbola are formed. So I'm not sure, I don't think you can actually see my mouse this time. For some reason this web page does not let you see my mouse, but I'm kind of hovering over here on the left where it says F1P, and here that's just saying the distance between F1 to P, so it's the segment length of F1P, and as you can see it's 4.5 units long, so each of these little tick marks, each box is actually half unit, so we have from F1 to P is 4.5 units long, and from P to F2 that's half of a unit long. So then underneath here on the left again, it says the absolute value of that segment length F1P minus the segment length of F2P. So we're seeing the difference between those. And the reason again it's doing absolute values because sometimes the distance of F2 to P is going to be larger, okay? Now if I hit draw here, okay, you can see all of the points on the hyperbola start to be graphed. So in red here is what we would actually graph as our hyperbola. So you're getting two different parts, the left and the right shape here. Now they're not actually parabolas, so avoid trying to call them parabolas because they're not actually parabolas, but they are U-shaped, those two parts of the hyperbola. But basically you see that the foci lie within those two U's, okay? And the distance, if I move this point P around, the distances between F1 to P and F2 to P, the difference between those distances remains constant. So even as I drag this point around, as you can see over here, when it says the absolute value of the difference, the distances here, that difference remains the same. It's always fixed at 4 units long, okay? So even when both of those segment lengths get really, really long, the difference between those distances remains fixed at 4, okay? So that constant remains the same. So I think this does a really cool job of actually showing you just exactly what that relationship is between the formal definition and what you see as you plot the points on the hyperbola. Okay, so let's return now one more time to our note sheet. We're going to go over some vocabulary terms, and I want to make sure that when you reference the parts of the hyperbola, you're using the correct terminology. So we'll go over the vocab terms, and we're also going to go over the general equations for the hyperbola. So I'm saying the word general equations, plural, because there's actually two different ones. So right here it should say general equations as opposed to just equation. So the reason why there are two different equations is because hyperbolas can open up and down, like the one you're seeing here to the right, but they can also open left to right, like the one that we just saw in that online graphing applet. Now, if a hyperbola opens left to right, then its general equation will be of the form x minus h squared over r sub x squared minus y minus k squared over r sub y squared equaling 1. So actually this looks really similar. If you're thinking that you recognize this equation, it's because it looks like an ellipse. The only difference is here we're using a subtraction sign in between those two terms as opposed to an addition sign. And it again relates back to the definition here of the hyperbola. I should probably erase the word sum here. Okay, now off to the side, I want to make sure you do draw a little sketch here. So if an equation is in this form here, then the hyperbola must open left and right. Now, another general equation is if the hyperbola opens up and down. Okay, so I'm going to draw in this little general sketch here. So if my hyperbola opens up and down, I know that the general equation is of the form negative x minus h squared over r sub x squared plus y minus k squared over r sub y squared equaling 1. So the equation looks pretty much the same, except for now the signs have changed to their opposites, right? This was plus, now it's minus, this was minus, now it's plus. So the signs are opposites of one another. Now, the way that I like to remember which equation goes with which sketch, because sometimes it's easy to confuse, does this equation go with this sketch or does this equation go with this sketch? So in order to remember which one goes with which, I like to look at the negative sign and where it is. So this negative sign is in front of a y squared term, okay? So it's in front of the y term. Now, if you think about a parabola that looks like this, y squared equals x, you remember when we graphed relations way back in the beginning of first semester, those parabolas opened left and right. So they either opened like that or like this. These were parabolas, and I know we're not calling a hyperbola parabola, but it's going to help you to kind of remember which general shape this hyperbola takes on. So when you see the negative in front of the y squared, it opens left or right, okay? When you see the negative in front of the x squared, that x squared, if we graph something that looks like that, this is a parabola that either opens up or down, right? So that's how I kind of easily remember it. I just think of the negative sign as the sign that dominates the hyperbola. So because the negative is in front of the y squared, this one would have to move, it would have to open left and right, just like a y squared parabola has to open left and right. And here, because the negative is in front of the x squared, I know that that has to open up and down just because I know that an x squared parabola opens up or down, okay? All right, so let's now focus in on the actual graph here and just label some parts. Okay, so here we have the graph of a hyperbola that opens up and down. Now off to the right here, I have a kind of general equation. I haven't filled it out completely yet though. So if that hyperbola opens up and down, remember that's like having an x squared parabola, so the negative should go in front of the x squared term, which means now that the positive must go in front of the other term here. So that would be the general equation for this particular hyperbola. Now, notice that we do have a center of the hyperbola, except for the center doesn't actually lie on the graph of the hyperbola. It's kind of weird, but we do need to draw in and actually graph the center, because that's how we determine where our vertices and where our asymptotes and everything else, where those end up. So we do need to graph our center. Our center is always at h comma k, okay, based off of the equation above. So once we graph our center, we can find the vertices of our hyperbola. Now, the vertices of the hyperbola are these two coordinates here. Okay, so let me label those. These are the vertices. Now, there is an r sub x and an r sub y here. Now, r sub y always runs up and down, okay? So that's going to represent the distance here between your center and your vertex. So this is r sub y. Now, what's weird is that in this case, r sub y does not have to be bigger necessarily, okay? Because the terminology also changes. We no longer call this a major or minor axis, so the distance between the two vertices is no longer a major or minor axis. We call this the transverse axis now, okay? So this is called the transverse axis. Now, the transverse axis does not necessarily run up and down every time. Okay, so the transverse axis changes. It can sometimes run left to right or up and down depending on how the hyperbola opens. So back here on your sketch, I'd like you to draw in that this is called the transverse axis here. It's the axis that connects your two vertices. And here, this would be the transverse axis. Okay. Okay, now back to our graph here. We also have to label the r sub x value. So I blew this up a little bit because it's going to be hard to kind of graph all of this all in one little sketch here. But r sub x is the distance from your center to one side of what we're going to call our hyperbola box, okay? So this is r sub x. And over on the other side here, this is also r sub x. Now, this forms, going all the way across, this forms another axis which we now call the conjugate axis. Okay, so that's the conjugate axis. So we have a transverse axis and a conjugate axis for the hyperbola. And once again, the conjugate axis does not have to run left to right every single time. It can also run up and down. So if we go back to our sketch, when your hyperbola opens left and right, your conjugate axis will run up and down. So right here, that would be what we would label the conjugate axis. Okay, and when your hyperbola opens up and down, then your conjugate axis must run left to right. And also, the length of the conjugate axis could be bigger than the transverse axis. That's why we don't say major and minor, okay? So please remember that we switch completely from major and minor because we don't have a bigger and smaller axis length. We just call them transverse versus conjugate to dictate how we open up our parabola. It's either opening up or down or left and right based off of which axes we label. Okay, so as I mentioned, we are going to form a box in order to graph our hyperbola. So the points that we found so far, the vertices that were dictated by r sub y here, and these endpoints over here of that conjugate axis, these will form, if we just connect here, if we go up the same number of units in the y direction and left the same number of units in the x direction here, we form a box. Okay, so this is the hyperbola box. Now, running through that box, as you can see, the diagonals form two lines, okay, which are right now dashed because these are asymptotes. Now, these asymptotes are special because they help us to graph the rest of the hyperbola, so let's make sure we understand how to actually find the asymptotes. Now, if you notice, I'm going to point out two different coordinates that lie on the graph of this asymptote here. Whoa, whoops. I don't know what just happened. I can't move this back. Sorry about that. Anyhow, if I look at those 2 points and I try to find the slope between those 2 points, I'm going to do change in y over change in x. So to get from this point here to this point, I'd have to go up r sub y units and then right r sub x units. So this represents the slope of this asymptote. Now for the other asymptote, if I did the same thing, if I look at this point here and the point over here, which lies on the graph of that asymptote, I'd have to go up r sub y units and left r sub x units, in other words, negative r sub x. So I have the slopes now of those two asymptotes. And of course, I already know a point, the center here, okay, that lies on the asymptotes, that lies on both asymptotes. So that would help me in writing the equation of both of those asymptotes, which we will get to in just a second. Now down below, let's just quickly fill in. Our center will always be at h comma k. R sub x is the x radius, while r sub y is the y radius. Okay, the slope of our asymptotes will always be positive and negative r sub y over r sub x. So it just depends on which asymptote we're looking at. One will be positive ry over rx, the other will be negative ry over rx. Now, the equation to find your foci is different than the equation that we used with the ellipse. So this is where students will make the most mistakes. They'll forget that this one you have to actually find, oh, what just happened again? You actually have to find the sum of r sub x squared and r sub y squared. Okay, so now we're ready to graph our first hyperbola. We have the equation y squared over 36 minus x squared over 49 equals 1. Now, because I have that negative sign here, I clearly know this cannot be an ellipse. So please make sure you're always looking out for when you have a negative sign. Some people will graph this as an ellipse, just not thinking straight. Okay, so one of the other things I think you should do too is just to rewrite this as negative x squared over 49 plus y squared over 36 equaling 1. I think always having the x squared term first might help you guys. But then think about how this opens. Now, because this negative sign is in front of the x squared term, that's going to dominate your hyperbola. So we think about what an x squared parabola looks like. An x squared parabola opens up or down. So that means this hyperbola should open up or down as well. So I always recommend that you start with a quick sketch before you actually go to graph the rest of your hyperbola here. Okay, so from our equation, we see that the center is going to be at 0, 0. So I'll go ahead and plot that now. And I still want to find r sub x and r sub y just like we did with the ellipses, and we'll do the same thing where we square root the value underneath the x term here to get r sub x, so we get 7. And when we square root 36, we get 6. Now remember, it doesn't matter which one is bigger or smaller. It doesn't dictate the major or minor axis, okay? Because we only have a conjugate and transverse axis here. Now, from this center, we want to go left 7 units and right 7 units. So I'm going to go left 1, 2, 3, 4, 5, 6, 7, and right 1, 2, 3, 4, 5, 6, 7. So that's my r sub x, and going in the left and right direction. I'll do the same thing for r sub y. I go up 1, 2, 3, 4, 5, 6 units, and down 1, 2, 3, 4, 5, 6 units, okay? And remember, these represent the vertices. The reason I know that those represent the vertices is because my hyperbola has to open up and down. I'm not going to actually draw this in, and you shouldn't either, because we don't know what that is supposed to look like quite yet, but those represent the vertices. Okay, so my vertices, let's write this off to the side here. The vertices are going to be at 0, 6 and 0, negative 6. All right, so now we want to form our hyperbola box here. That's going to just be a rectangle using those coordinates that we just plotted. Okay, so I create this box here, and that helps me draw in the asymptotes. So there we go. Here's our rectangular box. So I'm going to draw in the diagonals here, which would represent the asymptotes. So it's kind of hard to sketch this on a computer, but you do want to be accurate with this, so you can use a ruler. You can borrow my rulers in the classroom, but this would be, these two would be the asymptotes here drawn in. Okay, so one more thing we need to do before we finally plot this hyperbola. We need to find the foci, all right? And the foci will be found by solving this equation. F squared is equal to r sub x squared plus r sub y squared. So F represents the distance between the center and your focus. So F is distance between center and focus. So it's very similar to how we defined it with the ellipse. Now if I solve here, I have 49 plus 36 equaling f squared, which means f is equal to the square root of 85. So we know that our foci have to lie within the hyperbola. Okay, they're on the inside portions of the hyperbola. So we know that our coordinate has to be 0 and then root 85 and 0, negative root 85. So we have to move up root 85 units and down root 85 units. Now if that was something I could simplify, then you need to make sure that you do simplify that radical. But this also helps me to just approximate where we should plot that point. So that's in between 9 and 10 units. So we're going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9, and a little bit more. Okay, and then down 1, 2, 3, 4, 5, 6, 7, 8, 9, and down a little bit more. So notice I'm starting at the center. Whenever you graph your foci, it doesn't matter what shape, you want to start from the center. Okay, if it's the ellipse or if it's the hyperbola, always start from the center. Some of you get confused and you start from the vertex. So, all right, there's our foci, and I'm going to just label them F1 and F2. All right, so we've got our vertices, we've got our foci, and now when we graph our hyperbola, we just have to make sure that we follow the asymptote, okay? So this graph here is going to tend towards its asymptote, just like this. All right? And that is how we graph our first hyperbola. Now don't worry too much if this isn't beautiful here, but just try to make sure that it tends towards its asymptote. So as you know, x gets really, really big or really, really small, it's got to go towards those asymptotes. And these are called slant asymptotes because they're running on a slant as opposed to a horizontal or vertical asymptote. Okay, I almost forgot. We actually have to find the equations of those two slant asymptotes. So make sure that you do list your center, your vertices, and the foci, but you also must list the equations for the asymptotes. Okay, so the slant asymptotes here both have a slope of 6/7. One is positive 6/7 though. The other is negative 6/7. So this is the slope. Now this is not an equation. This just tells you what the slope of the asymptote is. It does not tell you the equation of the asymptote, and that's what we're looking for is the equation. So to find an equation of a line, because those are just lines, you need to find a point and a slope. We already have a slope. Now we just need to find a point that lies on the line, and the point that's easiest to use is this center here, because you can write two equations in one. So if I use the point 0, 0, and I just use point slope form, I take y minus 0 and set that equal to positive or negative 6/7 times x minus 0. So this would be the equation given for both asymptotes because one is just positive 6/7 and the other is negative 6/7, and they both go through the point 0, 0. Okay, in example 2, here we have a negative sign out in front of the y squared term. So we think about a parabola, and a y squared parabola opens left or right, okay? Which means that this particular hyperbola must also open left and right. So there's my quick sketch of this particular hyperbola. Now let's find some important information. We know the center is going to be at 3, negative 2. Our r sub x is 4, and our r sub y is 6. So let's go ahead and start plotting the center, 3, negative 2 here. Now the r sub x means in the x direction I move 1, 2, 3, 4 units, and left 1, 2, 3, 4 units. This is my transverse axis, okay, this segment length here. It's the segment that connects the two vertices. So this is a vertex, and this is a vertex of the hyperbola because it's supposed to open left and right, okay? Now for the other points that will form that box that we need to use, we'll go up 6 units and down 6 units from the center. So up 1, 2, 3, 4, 5, 6, and down 1, 2, 3, 4, 5, 6. Now for this box, let's connect these coordinates here. And we can draw in the asymptotes. So I would definitely expect you to be a little bit neater than what I'm doing right now, because I can't put a ruler on my computer. Okay, so there's the asymptotes. Now we need to find the foci as well, and then we can actually graph the rest of the hyperbola. So if f squared is equal to r sub x squared plus r sub y squared, we take 16 plus 36, then take the square root of that, and we end up with the square root of 52. Now, we do want to reduce this when we write the coordinate, so I'll write that as 2 root 13. So when I actually write out my foci here, think about which way you need to translate the center. So we're moving the center here, and the foci must lie to the left and to the right of that center. A lot of people will put it up and down, and then they'll graph the wrong hyperbola. So again, it's based off of your picture here. If it opens left and right, your foci should also be on the transverse axis, which runs left to right, okay? So we have to move the coordinate 3, negative 2, we have to only move the x value here. So we're going to move it left 2 root 13 units. Okay, so we take 3 and subtract 2 root 13. We keep the same y value. Let me label this as foci, sorry. I'll do it off to the side. So these are the foci. Okay, and we also want to move it to the right 2 root 13 units. So we have 3 plus 2 root 13, comma negative 2, and those give the coordinates of the foci. Now when you actually plot those foci, you want to go back to the fact that root 52 is much easier to approximate than 2 root 13. So if we approximate root 52, that's between 7 and 8 units, okay, because it's between root 49 and root 64. So we start from our center. We start from here, not from the vertex, all right? Very important. We start from the center, and we're going to move between 7 and 8 units to the left and 7 and 8 units to the right. So we go 1, 2, 3, 4, 5, 6, 7, and about like right here. That's one of the foci. Do the same thing on the other side. So 1, 2, 3, 4, 5, 6, 7, and a little bit over here. That's your other foci. So now we can draw in the hyperbola. Let's label that as F2. We can label the hyperbola and draw that in. It's going to tend towards its asymptotes, like so. Okay, and one last thing we have to do is find the equations for those slant asymptotes. So we know the slope of both of those asymptotes will be r sub y over r sub x, right? Which means it's 6 over 4, which I will simplify. Okay, so 6 over 4 simplifies to 3 halves. So the slopes here are positive and negative 3 halves. We know the center is 3, negative 2, so now we have a point that lies on both of the equations, so we can real quickly write the equation of the asymptotes using point slope form. It's going to be y plus 2 equaling positive and negative 3 halves times x minus 3. So those are the equations here of those asymptotes. Whoops, I forgot to do one thing here. I forgot to label the vertices. So for the vertices here, since we're opening left and right, we would translate our center by moving it left 4 and right 4 units. Okay, so our vertex, one of them should be at negative 1, negative 2, because I'm just going to subtract and add 4 to the x value. The other value, if I add 4, will give me 7, negative 2. So those are my vertices. All right, let's move on to the very last problem. All right, so here I would like you to try this one completely on your own. Notice that this is a little bit different because we have a less than or equal to symbol here. But think back to how we graphed ellipses with the less than or equal to symbol. We always tested a center. So if we test our center, we should always get 0 on one side, and then in this case is less than or equal to 1. Now, if you have a hyperbola, which I will just point out that the negative is in front of the x squared term. I'm not going to tell you how it opens. I want you to figure all that out on your own. But if you have a hyperbola here, and let's say it opens left and right, and you test the center, and in this case you get a true statement, well then you're going to graph where the center is. So it would graph like this, okay, where you shade in the parts that are not inside the hyperbola. Alright, so that's the end of the lesson. Please make sure you replay parts that don't make sense yet. I think as you graph more examples, it'll get a little bit easier, but there's lots of parts and it's different than the ellipse, so you got to really make sure you're working on your skills, okay? So come into class tomorrow ready to ask questions and prepared to work. Nice job. See you tomorrow.